medical center to rise on these grounds. This, as well as the other vast reaches of the city, where once lay the ugliness, the poverty, and sickness of slums, has been condemned and cleared. Such progress in medical facilities and research attracts the nation's leading doctors and surgeons. Typical of Detroit's spiritual heritage is the painstaking restoration of historic old Mariners Church. Here is reflected the city's many old and new churches and synagogues. Detroit, an exciting place to be, to live, to grow, to work shoulder to shoulder, regardless of national origin, color, or creed. Detroit has earned an outstanding record in community relations, a reputation which is nationally recognized. Here are found 92 ethnic groups, more than in any other major American city. Small wonder Detroit is a foremost city in international relationships. Detroit's progress in good ethnic relations owes a great deal to International Institute, the largest of its kind in the nation. Here is a focal point for the multiracial strains that compose so much of Detroit's population. International goodwill is perhaps experienced most frequently at the border between the United States and Canada. Thousands go back and forth daily between Detroit and Windsor, Ontario. Such comradeship is underscored by the International Freedom Festival.
Both ways before crossing the intersection. And always give pedestrians the right of way in crosswalks, because we move so much faster than they do that they might not be able to get out of our way. And we also learn that it's just as important to keep our bikes in good condition as it is to keep up a car.
Especially the brakes. They're the most important part of the bike to keep in good shape. If you can't get going, you can't get into much trouble. But once you're going and you can't stop, boy, you've really got trouble.
You're absolutely right there. You know, I've been wondering about something. Is all this just a lot of fancy talk, or do you really drive your bikes?
Honest, Dad, we really do. We found that by driving our bikes, we keep ourselves out of a lot of trouble. Why, just the other day as I was going to school, I had an experience where driving my bike sure helped me. I was late getting started, and really had to hurry so I wouldn't be late for school. I thought I'd save time by cutting through the alley from Oakwood to Pine. You know that alley. Well, I was riding as fast as I could, but as I came to Pine Street, I suddenly thought, would I drive a car out of this alley into Pine Street as fast as I could go? That made me realize that it would be a very dangerous thing to do, so I slowed down and looked to see if anything was coming. And it's a good thing I did, as the car was coming down Pine Street and the driver wouldn't have seen me if I'd ridden out of the alley as fast as I was going without looking. I still got to school on time that morning, but if I hadn't been driving my bike, I might not have gotten there at all. So, driving my bike helped me avoid an accident and kept me out of trouble that time.
Yes, I can see it paid off in that case.
I had an experience like that one, except that I was able to keep from hurting someone else by driving my bike.
Oh, what happened, Bob?
One day I was riding along Kenneth Road. I'd just come down the long hill from Adams and had gotten up speed to make the long 2-block climb up to Washington. I was making good time when I saw 2 girls starting to cross the street. I knew if I stopped and lost my speed, it'd be a tough pump to get to the top of the hill. But I thought about driving my bike and decided what I'd do if I were driving a car, which was, of course, to stop and wait till the girls had crossed. It was lucky I saw them and stopped, as they might not have seen me, and might have walked right in front of me. And when a car also stopped, it made me feel pretty good to know that I'd set an example for that driver.
Wasn't that good feeling you got from being courteous and considerate worth the extra effort it took to get...
Leaping and winking fireboxes. Intense heat. The flames roar in the furnace, yet the oil flows so fast the heat does not scorch it. And scientists wrest from the crude petroleum its tremendous power in the form of gasoline and other fuel oils. And that's done in these towers called fractionating towers. They divide crude oil into the lighter and heavier parts. Those of different boiling points liquefy at different levels in the towers. Some lighter than gasoline liquefy at the top. Heavier parts liquefy further down. At the bottom are the heavy fuel oils, or the raw materials from which lubricating oils are made. When increasing use of motor cars pyramided the demand for gasoline to extraordinary heights, scientists were called upon to devise new methods. How could a greater proportion of gasoline be extracted from the crude oil than that obtained from the fractionating tower alone? To meet this challenge, the scientists turned to products other than gasoline which are drawn from the crude, studied their molecules, and found a way to change them, to turn them into gasoline. The result was cracking. Let's look at a diagram of a cracking plant. Here we see how one part of petroleum that is not gasoline is converted into gasoline. Called gas oil, it is pumped through a pipe into a cracking furnace, heated to over 900 degrees under tremendous pressure. And the individual particles, molecules, are broken into smaller molecules, just as coal is broken under a hammer. If we could see one of those molecules, it would look something like this. The hotter the molecule...
Steel road building machines have been developed. One such machine is the drag scraper. It scoops the dirt off the high spots, carries it along, and deposits it in the hollows in one operation. Power shovels of many standard and special types dig away the earth and expose rock formations. These obstructions were spotted previously by the surveyors and now must be removed to bring the highway to the established grade. With modern equipment, it's more economical to blast them out of the way than to go around them. Air-powered drilling machinery bores into the rock, making holes for dynamite. The drill itself is hollow, and the blast of air forced down through the center blows the rock dust out of the hole. It's a faster operation than the old way and gives a truer hole for the explosive. After the required number of holes have been drilled in the layer of the rock, the dynamite is carefully tamped into place. And when the area is cleared, after the dust settles, men and machines dig in again, scooping up the broken rock. In this type of work, equipment really takes a beating. Wire rope, a few hundred pounds of it installed on a 30-ton shovel, is the steel member on which the whole mechanism depends. Wire rope is strong and resilient, must withstand the highly abrasive atmosphere of the construction project, and must not fail when subjected to repeated flexing over small shivs and drums. As manufactured today by Petroleum Steel Company, wire rope gives outstanding service under hard usage. Modern highway design does not tolerate grade crossings. In most cases, where a railroad or another highway is encountered, either underpass or overpass is provided. In bridge construction, concrete piers are reinforced with steel bars. The protruding ends are left long enough to be bent over and tied into the bridge deck. In either piers or pavement, a firm bond between steel and concrete is assured by the deformations rolled into the bars. Petroleum Steel Company maintains reinforcing bar fabricating shops in all major highway construction areas. Road building materials are stocked at these locations. As needed, reinforcing bars are cut to length and bent to shape. In any mass of concrete, certain lines of stress develop, and the bars are carefully bent to follow these lines, so that they will bear their full share of the load on the completed structure. Used in all kinds of concrete work, reinforcing...
22, Metropolitan undertook, on an experimental basis, its first housing project in the borough of Queens, New York City. With the background of this experience, the company in 1939 started construction of Parkchester in New York City, the largest housing project ever built in the United States. This was followed by another project, Park Fairfax, just outside of Washington, D.C., which helped meet an acute wartime housing shortage in the nation's capital. Still other projects, Park Merced in San Francisco, Park La Brea in Los Angeles also helped meet wartime housing needs.
the plan of the structure became apparent and soon extended along its full 660 feet dimension of thickness at the base. Throughout the lower levels of the structure, concrete was placed from a trestle anchored to the Nevada wall of the canyon. The concrete was poured in keyed or interlocking columns, the design of which became more noticeable as the 5-foot layers or lifts in which the concrete was placed rose from level to level. As the work of placing progressed, the crews became expert in the handling of the equipment, and record-breaking daily pours were made, only to be surpassed by later achievements on this same structure. Transit mixers were transported on trucks, from the bed of which they could be removed and handled on the overhead cableways. These were used in the placement of concrete in the confined forms along the abutments, where the 8 cubic yard buckets could not be handled. Selecting at random one bucket from among the hundreds of thousands that traveled from the canyon rim over the cableways and down into the dam forms, we see the typical operation from the time the bucket is picked up by the cableway on the canyon rim, swung out into midair over the gorge hundreds of feet above the forms, its tremendous weight of 22 tons riding easily and gracefully over the cable, as it is lowered into the forms with an ease and certainty seemingly out of proportion to its great bulk and tonnage. As the bucket descends, suspended at the end of hundreds of feet of cable strands, it is received at the forms, the safety locks unlatched, the signal given, and 8 more cubic yards of concrete added to the dam's bulk. Concrete was compacted into the forms by mechanical vibration, the application of which ensured dense compression against adjacent surfaces. Workmen were carried from the canyon rim to the dam forms by way of the inclined skidway, or monkey slide as it was called, which operated through the Nevada abutment excavation. Boulder Dam laborers represented a fair cross-section of the American working class, and many stayed on the job during the entire period of construction. With an ambitious progress schedule to meet, and with work going forward under all conditions at all seasons of the year without cessation, rain or shine, both day and night, within a year, less 4 days, 2 million of the 3 1/4 million cubic yards of the dam's total volume had been placed in the forms, and Boulder Dam had risen to an impressive height, already having taken its place as one of the wonders of the West and a tourist attraction of prime importance. Meanwhile, progress had been made in the erection of the structures appurtenant to the dam itself. The construction of the power plant, a U-shaped structure at the downstream toe of the dam, had been in progress for some months, and as its substructures assumed form, it gave some hint of the beauty it was later to possess. The intake towers, 2 on each side of the canyon wall immediately upstream from the dam, were in course of construction, and from a maze of reinforcing steel rapidly rising toward the uppermost rim of the canyon. These structures were later to serve as...
The size of the dent or impression is measured under the microscope. The smaller the dent, the harder the steel. A microscope isn't needed to compare the size of the dents made in hard chromium steel and ordinary steel. Some uses of steel require it to be extremely strong, able to withstand tremendous strains. The strength of metals is measured by pulling test pieces apart in a powerful machine. The dial of the testing machine shows the tremendous force used in pulling apart a piece of plain steel. More and more force is used. The steel stretches under the load and then finally snaps. More than 13,000 pounds of force are required. Plain steel can be made stronger by adding nickel in addition to a small amount of chromium. Now let's see what happens when the chromium nickel steel is tested in the stretching machine. The bar breaks. Our chromium nickel steel test piece is more than twice as strong as common steel. Great heat weakens common steel, but some steels today have to stand up under great heat and still keep all their good qualities. Steel can be given an ability to resist great heat by the addition of a little chromium and also some silicon, the element which is found in ordinary white sand. Under constant bending or vibration, all ordinary steels have a tendency to become fatigued or tired. In the laboratory, the fatigue strength of metals is measured by placing a test bar in a machine which in a short time duplicates the effect of years of use. By adding a little bit of nickel and a small amount of a metal called molybdenum, plain steel can be made to stand up for years and be practically tireless. For certain conditions, a steel is needed that will be very hard on the outside and tough on the inside. A little carbon added to the outside of steel gives it a hard surface and leaves the inside tough and strong. This process is called carburizing or case hardening. By special photography, we can see what happens to a piece of steel when it is completely surrounded by small particles of carbon-bearing material. When heated, the steel slowly soaks up the carbon to form an extremely hard surface. This adding, mixing, and combining of plain steel with friendly little fractions of other metals to improve its qualities is called alloying. Chromium, nickel, silicon, molybdenum and vanadium, tungsten and manganese. All these tough friends have improved these
time products. Progress anywhere in America is good news for all of us. And so United States Steel proudly plays its part in the amazing industrial development of the Far West. In Geneva, Utah, it has purchased the plant it designed, built, and operated for the government without fee or commission during the war. The wartime production of plate for ships has given way to the production of hundreds of thousands of tons of steel for peacetime uses in the Far West. In Pittsburgh, and this one is in California, there's a brand new mill. It's a cold reduction mill designed to keep pace with the rapid tempo of the Pacific coast. Steel products can speed through these new machines at the rate of 35 miles an hour. More than 300,000 tons of tin plate and sheet steel every year. This brand new mill provides a major source of supply for Western agriculture and industry. There's another one scheduled in Los Angeles. Now, as always, United States Steel maintains a fair and equitable policy of distribution. Buyers of tonnage lots order direct from the producing companies. Others rely on warehouses. United States Steel has built a new one in St. Louis. 3 more are opening in Cleveland, Los Angeles, and San Francisco. Throughout the land,
lumber in the north and coal in the hills. Iron and coal down the Monongahela. Iron and coal down the Ohio. Down to Pittsburgh. Down to Wheeling. Iron and coal for the steel mill. For the railroads driving west and south. For the new cities of the Great Valley. Omaha and Kansas City. Across to the Rockies and down from Minnesota, 2,500 miles to New Orleans. We built a new continent.
The wind blows west from the Great Lakes. The wind sings like a wild bird across the northern states, coming at last to this place, this sweep of America. 10,000 square miles of prairie across Montana and Dakota. They call it the Williston Basin. Not so long ago, this was frontier. Listen closely, and you will hear the old ghost echo of covered wagons, the phantom shadows of pioneers fighting for their lives against the wilderness. Lean men hard as hickory, lonely women wearing their dreams like a bit of bright calico. They began with nothing, with
somewhere, with someone on the job. Everything we have is started. Somewhere, on some fertile acre, the plow knifes through soil that abounds in promise. And the farmer, although he plows alone, is not alone. His life is tied in with the lives of many others, of all of us who depend on him and on his mechanized labors. And he, in turn, depends on all of us. Somewhere on a lonely range, the earth trembles under the hooves of cattle on the move. And the man who rides the range alone, if he listens with vision, can hear in the rumble of the herd the beginnings of the rumble of distant machinery in the factories where others will finish the work he has begun. Somewhere, someone sets a blast to erupt rich ores of metal from stubborn rock, and sets men to work in smelter and in blast furnace, in mill and in factory. And thereafter, people, many interdependent people, come to fashion the products of human inventiveness from all the bounty of nature.